In this video, we're going to take a brief look at the 6 crystal systems using these two very nice diagrams from the online mineralogy textbook of Dexter Perkins. So the reason why the crystal systems are important to know is because if you look up a mineral, let's say you look up forsterite or olivine, the first thing you will see most likely is a formula. So this would be the mineral formula for forsterite. But the very next thing most books will note is the crystal system, and usually it'll be abbreviated by taking the first couple of letters, or they might spell out the whole thing. So if you see ORTH, that is for the orthorhombic system. That means if you take magnesium, silicon, and oxygen atoms and pack them together, they'll make some kind of arrangement like this. Actually, not just any of those. It ends up that Dr. Perkins is showing the olivine structure here. So if we had a forsterite crystal, it would grow something like that. But all the minerals that occur in any particular one of these systems, the orthorhombic system, just to take this example, all have something similar in terms of their ordered atomic arrangement of atoms. So let's take this other diagram. Let's say we have atoms in solutions. They're not tightly bonded together. Well, they are kind of quasi-tightly bonded in terms of a liquid. They might be dispersed, but they don't have an ordered atomic arrangement. But as they begin to order themselves, we have this process of nucleation. And with nucleation, we make nuclei. Nuclei are the smallest bits of matter that have some kind of discernible ordered atomic arrangement of atoms. And as this material grows, then we get a full-fledged crystal, which is shown down here. Euhedral, by the way, is just a Greek term to say that this is a very nicely grown crystal, and it has well-developed faces on all of its sides. So for this cube, it would have very nice six-sided shape. It'd be a collector's item if you found something like that in nature. So this would be something that would look something like this guy here. There's a little bit of a depth of field issue, but imagine that this edge is the same length as that one, is the same length as that one. And in another video, we talk about crystal axes where we follow up on these 6 crystal systems. But we don't necessarily have to make this cube. We could take the very same internal atomic arrangement but make other kinds of shapes. So how many different kinds of shapes can we make with this kind of arrangement? Well, take a look at these blue guys here. So let's say that instead of making a flat face the way we've shown it here, let's say we have a face that's created from those blue minerals. And so we strip off all those guys here, and then we'd have a face that is kind of triangular in shape, still flat. You might imagine that that might hook up with another face over here that is also triangular in shape. And you could see how by the very same arrangement, the same internal atomic structure is shown for this cube, you can not only get this structure here, but you can get that one there. And so the cubic system collects all those different kinds of shapes that you can get starting from this basic arrangement of atoms, depending on whether you grow faces the way they're shown here, or whether you take an array of atoms and then create a face by growing out in this direction instead of perpendicular to these flat sides. So depending on how this crystal grows, how it likes to grow, how the atoms are, the strength of bonds between the various atoms, you can get these various shapes. Now, if you have a different atomic arrangement, you could start getting different kinds of shapes. So with the tetragonal, it's kind of like a cube, except the cube is stretched out in the vertical direction. So this is going to have a square cross-section, but it won't be square in this direction here. It's been stretched out in the vertical. Then we could take that tetragonal and stretch it out in the horizontal direction. And if we did that, stretching it out, let's say side to side or front to back, then we'd have the orthorhombic system in this collection of shapes. And then with the hexagonal, hex means 6, and that means that if we, let's take this guy here, the quartz crystal. If we have this crystal shape here, we can rotate it in that direction, and then this face here would repeat 6 times if we rotate it around that vertical axis 360 degrees. With rhombohedral, it's a little bit different. If we rotate around this vertical axis, we'd repeat this kind of face here 3 times instead of 6. With monoclinic, we lose a lot of that rotational symmetry that, again, is better left for another video, but you can see mirror planes coming out here. I'm going to draw a mirror plane along that edge, etc. And then when we get to the triclinic, we lose everything. There are no mirror planes, so no M's, There's no rotational symmetry, so no twofold, threefold, fourfold axes, sixfold axes of rotation. We lose all the symmetry altogether, so we have a much more disordered atomic arrangement of the atoms. So those are the six crystal systems, or if you want to consider rhombohedral and hexagonal would be different, we can cross that out and call them the 7 crystal systems. No matter, the important thing is to understand that these names are ways of classifying related shapes. Of course, these shapes are not exactly the same. We have other kinds of terms to describe these and other ways of describing their internal atomic arrangement, but they have fundamental characteristics that are similar in terms of the way these things are built out and their ordered atomic arrangement. So those are the 6 or 7, if you prefer, crystal systems.